Good morning. Today, we are going to study how to determine the hybridization of the central atom of a molecule using group theory. So, we can move on to the topic, that is determination of the hybridization of the central atom of a molecule using group theory. In order to find out the hybridization, first of all, we have to determine the point group of the molecule. That is, the first step is to determine the point group of the molecule. And in the second step, that is by considering the sigma bonds as bond vectors, we have to determine how many of the bonds are shifted or the number of bond vectors remains unshifted. And this is done by the symmetry operations of the group. Then as a third step, we have to obtain the characters for the bonds. That is the number of unshifted bond vectors. And in the fourth step, by using the standard reduction formula, we have to reduce the re-reps into a linear combination of the e-reps from the character sets of the point group. So we can move on to the procedure, and we are taking the first example of BF3. As we are going to find out the hybridization of boron in BF3 molecule. Okay, so first of all, we have to find out the point group of the molecule. And we all know that the molecule is trigonal planar and belongs to the point group D3H. And next we have to consider uh, the bond vectors present in it. And from here it is clear that in BF3 there are three sigma bond vectors. That is the first one BFA, second one BFB, and the third one is BFC. Three bond vectors are present. Three bond vectors or three sigma bond vectors are present. Bond vectors are present in the BF3 molecule. So now we know that BF3 molecules belongs to the D3H point group and it contains three sigma bond vectors. We can move on to the next step. That is the next step. We have to copy the character table from the literature. We have to copy the character table for the D3H from the literature. And it will be like this. D3H, the symmetry elements are E, 2C3, 3C2, sigma H, 2S3, and 3 sigma V. And we have the E reps A1 dash, A2 dash, E dash, A1 double dash, A2 double dash, and E double dash. Okay. Next, we have to find out the number of unshifted bond vectors. For determining hybridization, we have to find out the number of unshifted bond vectors, or it will give the characters for the reducible representations irreproducible. So we have to consider the three bond vectors, and here we have a schematic representation of the BF3 molecule. And now we can find out what will be the reducible representation for the BF3 molecule. For that, we have to consider each and every symmetry operation. And the first operation is identity operation E. Identity operation means doing nothing. That is, we are doing nothing on the molecule. That is, the molecule will remain as such. Or on doing E, none of the bond vectors are shifting their positions. They will remain as such, and the number of unshifted bond vectors will be equal to 3. Then the next one is 2C3. That is rotation around 120 degree of rotation. And this will be the C2 axis of rotation that is passing through the boron atom. And on rotating, all the three fluorine atoms will be changing their positions. We can say that all the bond vectors are changing their positions and the number of unshifted bond vectors will be equal to 0. So on doing C3 operation, the character for reducible representation will be 0. The next operation is C2. And the C2 axis is this one that is passing through the central boron atom and one of the fluorine atom, this one. And here also we have boron and fluorine atom, and this will be also a C2 axis of rotation. And this will also a C2 axis of rotation. So we can say that there are three C2 axis of rotation passing through the central boron atom and each and every fluorine atom. On taking the C2 axis of rotation, that is, this is one is the C2 axis of rotation, these two bonds will be shifting their positions or interchanging their positions. Or we can say that only one bond vector remains as such. Only one bond vector remains as such, or the represent character for the reducible representation for irreproducible for C2 operation is 1. The next operation is sigma h. That is, it will be the plane perpendicular to that of the principal axis. And we all know that the principal axis is the C3 axis that is passing through the central boron atom, and perpendicular to it we have this plane. This will be the plane. Or we can see that the sigma h axis will be cutting through the central boron atom and the 3 fluorine atoms, or it will cut the molecule into 2 equal halves. On taking the mirror image, the down part will become upwards and upwards will come the downwards. Or we can say that none of the bonds are shifting their positions. All the bonds remain in their positions, and therefore the contribution will be, or number of unshifted bond vectors will be equal to 3. On doing S3. What is S3? S3 is improper axis of rotation. That is rotation followed by reflection. Here S3 means C3 rotation followed by the reflection. On C3 rotation, we can say that all the 3 bond vectors are shifting their positions. And then taking reflection, the same will be the effect. And we can say that none of the bond vectors will remain as such in position. Or we can say that the contribution will be equal to 0. And the next operation is sigma V. Sigma V plane that is passing through the principal axis, and this will be the sigma V plane, or it is similar to that of the C2 axis of rotation. This will be the sigma V plane, and this will be the another second sigma V plane, and this one will be the third sigma V plane. First sigma V plane, second sigma V plane, and the third sigma V plane. Or we can see that taking reflection along this axis, these 2 bond vectors are changing their positions, whereas this one remains as such. So we can see that on doing sigma V operation, only one vector remains in the position, and the number of unshifted vectors will be equal to 1. So these are the characters for reducible representations. To find out the hybridization of boron in BF3 molecule. And we can see that the reducible representation is equal to 301, 301. And now we have to reduce this representation by using standard reduction formula. And we know that the reducible representation is a combination of the EREBs. And the standard reduction formula is Ni is equal to 1 by H into sigma C GOC character of I into character of R. And you can look at the terms. Ni is equal to the number of times an irreducible representation I occurs in the reducible representation. That is, we know that reducible representation is a combination of the EREBs. And here Ni means how many times each EREB is repeating to form the reducible representation. And next we have H. H is the order of the group. We can see that it is equal to the sum of the symmetry elements present in the group. For example, for C2V point group, the symmetry elements are E, C2, sigma V, and sigma V prime. So we can say that it contains, or the order of the group will be equal to 4. And now C. C is the class type of operation. That is which operation we are taking. And GC. There's a number of operations in the class. That is, we have already seen that there are 2 C3 operations. So GC for C3 operation will be 2. And 3 C2 operations. For C2, the value GC will be equal to 3. Next one, character of I. Character of I is a character of the irreducible representation. That is, if we are taking the A1 dash EREB, the character corresponding to E in the A1 dash EREB, it is taken as the character I. And next we have character of R. This is a character of the reducible representation that we got as 301, 301. Okay. And once again, we are writing the standard reduction formula and the character table. And now here we have calculated the order of the group H is equal to 1 plus 2 plus 3 plus 1 plus 2 plus 3. This 1 plus 2 plus 3 plus 1 plus 2 plus 3 will be equal to 12. And on reducing each and every operation, that is, if you want to find out the number of a1 dash, n a1 dash is equal to 1 by 12 into sigma g of c character of I into r. If you are taking the e operation, 1 into e reverse 3 plus 2 into 1 into 0 plus 3 into 1 into 1 plus 1 into 1 into 3 plus 2 into 1 into 0 plus 3 into 1 into 1. And on reducing, we will get the answer will be equal to a1 dash. And similarly, we are calculating the number of each and every error. And the result will be equal to for the error reducible representation reduces to a1 dash plus e dash. Or we can say that the orbitals used in the hybridization of BF3 molecule, it must have the symmetry a1 dash plus e dash. It must have the symmetry a1 dash plus e dash. And by taking the atomic orbitals corresponding to these errors, we can find out which type of hybridization is present in the boron atom. And for that, we have to look at the sixth and seventh area of the character table. Here, sixth area, we know that it contains what? Single functions, and the seventh area contains binary functions. So we can look at A1 dash. Here, the sixth area is empty, and the seventh area contains the function x square plus y square z square. X square plus y square z square. X square plus y square z square. That is, it is equal to x square plus y square z square is equal to s orbital or totally symmetric orbital s orbital. And for E dash, we have xy, x square minus y square, and xy. Here, xy in the sixth area indicates px, py orbitals, and x square minus y square, xy indicates which one? Dx square minus y square and dxy orbitals. Okay, we can continue. That is, A1 dash contains x square plus y square z square orbital, z square, which means that a totally symmetric orbital and it is equal to the s orbital. And in the E dash orbital, we have x and y. Sixth area, we have x and y. Here, x, y, and z shows the px, py, and pz orbitals. So E dash contains px and py orbitals, and in the seventh area, it has x square minus y square and xy. It indicates the d orbitals, dx square minus y square and dxy. So we can say that from the A1 dash and E dash orbitals, or it corresponds to s orbital and two p orbitals and two d orbitals. That is, by knowing the errors which are contributing to form the errors, we can find out which of the atomic orbitals are present. And this process is known as transformation properties of atomic orbitals. Okay, there is x square plus y square z square. It is transforming into the totally symmetric s orbital x and y. It indicates the px and py orbitals, x square minus y square and xy. It indicates the dx square minus y square and dxy. And this property is known as transformation properties of atomic orbitals. And so we can see that one s orbital and two p or two d orbitals are combining to give the hybridization of boron in BF3. And so the hybridization may be sp2 or maybe sd2. And here we have BF3 molecule and the boron atom in its valence shell have p orbitals. And we can see that the three three x square minus y square and xy orbitals, that is dx square minus y square and dxy orbitals, is too high in energy to hybridize. So here the hybridization of boron in BF3 molecule will be equal to sp2 with diagonal planar geometry and bond angle 120 degree. Thank you.